Hello everybody, today I'll continue my discussions on distributions of objects. Please be patient with me. Okay, so last time we saw two things. One, that the number of distributions of indistinct objects into distinct boxes where none of the boxes was left empty to be equal to b equal to k factorial times s and k. Remember? And then using that, we also counted the number of ways and distinct objects could be distributed to k distinct boxes to be equal to the sum k varies from j varies from 1 to k of pkj times s and j. Okay, and then I mentioned to you that this number is nothing but k to the power of n, though I haven't discussed why that happened or why or how that is possible when that is really very simple to explain. Okay, so the first thing I'm going to do today is 1, explain why that equality or that relation, explain the last relation we have, and the second one is determine the formula to compute Stirling numbers of the second kind. I mean, well, we have a table, but we need, it would make life easier to be able to compute those numbers in terms of actually given in terms of simpler expressions. So, the first one, consider the distribution of n distinct objects into k distinct boxes. Okay? Now pick an object. Pick any arbitrary object among those n. Now, and you want to throw it in a box. Okay? And we do have k distinct boxes. How many different possibilities does it have? Or how many possible choices or how many choices of boxes does it have? It's very obvious and easy that any of the objects to be distributed has k different possibilities. Okay, to be in box 1, to be thrown in box 2, in box 3, or in box K. Okay, so each of these objects has K possibilities. Therefore, it follows. Actually, picking, let's say, the third or the fourth object, okay, and throwing it to a box does not depend on any of the things that I've done before it becomes the turn of that particular object. So it's quite independent. It will equally have K different choices because actually the capacities of the boxes are not limited. Okay, they can take all the N objects and they can remain empty as well. Therefore, it follows that there are, by multiplication principle, K times K times K times K, which is K to the power of N, because I will do it for the once for every object of the N, therefore K to the power of N different ways. Now you see that the number of distributions of N distinct objects in K distinct boxes is K to the power of N. Now, since we have counted the same set of distributions and we came up with two results, one is K to the power of N and the other one was a sum of the products of P, Kj, S and J, it's evident that those two quantities must be the same, must be equal. Okay? We counted the same thing in two different ways, came up with two numbers. Those numbers have to be the same. That's why we have the relation. The sum Pkj times S and J as they run from 1 to N to K is equal to K to the power of N. That's explained. Okay, now let's go to the second task. Second task is to compute S and K. Good. Now I'm going to partition the set of all distributions of N distinct objects into K distinct boxes into two, partition it into two. Obviously then one will be the complement of the other. Okay? So I have a formula one in terms of Stirling numbers. Then I will be able to explain or to express the other one, its complement, as the union minus the set. And that will give me a formula to compute the Stirling numbers of the second kind. Good. Now, you see, let S be the set of all distributions, the set of all distributions of N distinct objects into K distinct boxes where no box is left empty. Okay? No box is left empty. We know how to count this. We have a formula in terms of Stirling numbers of the second kind. And we have seen that. We've seen that given by k factorial times Snk. Now we are going to count the complement. What's the complement? Well, obviously, S bar is a set of all distributions of n distinct elements or objects into k distinct boxes where at least one box is empty. Okay? This is the set of all distributions of the n distinct items into the k distinct boxes. Okay? Where at least one box is left empty. At least one box is left empty. Good. Now let me further explain S bar. It will produce some more notations, okay? So let, to be specific, let Bj stands for the subset of S bar, meaning the set of distributions of n distinct objects into k distinct boxes where the ice box is empty. Bj equal to the J's box. Okay, the J's box is left empty by those distributions in Bj. Okay, what does that mean then? What does that mean? That means that S bar is the union of the Bj's. So, by definition, follows that S bar is nothing but the union of J bar is from 1 to k minus 1 of the Bj's, because you see I haven't included the k because there is no distribution which leaves all the k boxes empty. In that case it wouldn't be. Okay, so we are not interested in that. So S bar, even if I put that, it has to go to 0. It has to be 0 anyway. Now, S bar is this union. Now, we need the inclusion-exclusion formula to compute the union, to compute the size of S bar, because that is what we are interested in, because that will give us, because those two numbers will add up to the size of the universe, which we know already, and from that we can obtain a formula for the Stirling numbers of the second kind. Say the whole universe is here. We know that this is k to the power of n. When here we have s, we know that the size of s is k factorial times snk, and that is what we are looking for. The size of s bar. Here is s. That's what we're going to do. Good. Now, let me just illustrate or try to remind you of the inclusion-exclusion, okay? So we are going to need some more notations. Okay, let Sm denote the sum of the size or the sizes of m-tuple intersections. That means the sizes of all such intersections, B1, B2, up to Pm, the intersection. Okay? all possible such n-tuple intersections, the size of all the intersections. So Sm is a number for every, okay, up to m minus n could go up to k minus 1 in our case. So for in general for inclusion-exclusion it goes up to k. Now if that is so, the inclusion-exclusion formula says the size of the union of the bj's is nothing but S1 minus S2 plus S3 minus S4 and so on. Okay, S1 minus S2 plus S3 minus S4 and so on. Then plus minus 1. So the last one, if it is k minus 1, so it will be raised to k. Before raised to k minus 1, raised to k is k minus 1. Because this j bar is from 1 to k minus 1. That's what it is. So now we'll limit ourselves, okay, in computing these numbers. What are these numbers? I mean, we can determine the numbers based on the definitions of our BJs. What is BJ? BJ is a set of all distributions of n distinct items with k distinct, where the j's box is empty. Okay? So from that, S1 is simply the size of B1 plus B2 plus the size of B3 plus the single set. I mean, there are no intersections here. So in that case, what I have to ask is, in how many ways can I pick this one box that's going to be left empty? So there are k possibilities. It could be box 1, box 2, or box k. So I do have k choose 1 ways to pick this one box to be left empty, and then I'll be left with, or the job of distribution or distributing n distinct items into k minus 1 boxes, which we have already established to be k minus 1 to the power of n. There comes the minus. Now, this is a case of 2 boxes being left empty. There are solutions which leave 2 boxes empty. Okay? So, obviously, I will have k choose 2 times k minus 2 raised to n. This way, it goes on this way, and here I will have minus 1 raised to k. I have k choose k minus 1. We have k minus 1 empty boxes with 1 box, so 1 to the power of n. There is only one way to do that. See, this sum is the number of ways n distinct items could be distributed into k distinct boxes. Okay, where at least 1 box is left empty. So that means we have counted S bar. We have counted S bar. Don't forget that the size of S is obviously the size of the universe minus the size of S bar. And that would give me the size of the universe is k to the power of n minus what I have there. Kj, k minus j raised to n. This would be minus 1 raised to j plus 1. Kj, k minus 1 or k minus j raised to n. Okay, I forgot to write the sum, sorry. Minus the sum, j varying from 1 to e minus, okay, sorry, to k minus 1. Okay, when this is k minus 1, this will be 1. K minus 1, this will be k, and so on. See, this is what happens. This is a formula for what we have established to be k factorial is nk. Therefore, it follows that our Stirling numbers of the second kind could be obtained by dividing that by 1 over k factorial. So 1 over k factorial times k to the power of n minus the sum j from 1 to k minus 1 minus 1 raised to j plus 1 kj k minus j to the power of n. See, that's what we obtained. Well, it could be simplified, or it could be expressed as is nk is equal to 1 over k factorial times k raised to n plus, you can write it as here minus 1 raised to j or j plus 2 or j then times kj k minus j to the power of n. J varying from 1 to k minus 1. That's what I promised, right? So I think I will continue from this next time. Thank you for